Okay, so here's where we were last time. So yeah, finally getting around to defining the cross product of two vectors. Now recall we've already defined something called a dot product. That's different, right? Different thing. Okay. So the cross product, here's the notation for it. By the way, notice that we are again ripping off an old notation for times. Right? This is a different kind of older notation, maybe that maybe you abandoned back in elementary school at some point for how to multiply two numbers. And here's the formula. It's it's an even weirder formula than the formula for the dot product. Right? Very hard to see why this would be anything of interest at all. The development that leads to this is there's a bunch of work that goes into this, right? So it is absolutely not expected that you should look at this and think, yeah, okay, I get that. Right? Not at all. Not at all. Okay. One other little reminder. Notice that this is defined only for vectors in R3, specifically 3. Right? This is just in R3. Okay, so it's not like the dot product in that sense. For the dot product, you can, two vectors of any dimension, you can do their dot product. And it's the formula is pretty much the same. Analogous, certainly. Here, no, just in 3 dimensions, 3 only. Okay. Right, so that being said, here's some algebraic properties. Now, we tend to look at algebraic properties and just kind of yawn and go along. Let's be careful in this case. Notice this is not just like a formula that you saw back in elementary school. This is pretty inconsistent looking with that, right? So all of a sudden you see maybe why it is that mathematicians are uptight and careful of writing down what kinds of rules of algebra do we have to work with, because sometimes we don't, right? We want to make sure that we don't just start writing down garbage because it looks good, right? So here, pay careful attention and notice that if you switch the order, and you're going to want to say, it's a multiplication. Come on, multiplication's commutative, right? No, it's not. Anti-commutative. Okay. All right. So, side note, that is actually kind of interesting, right? I mean, it's nice to be able to say that you can just kind of switch the order. Commutativity is neat, but the fact that you get exactly the negative when you switch the order, it's an eyebrow raiser. Right? It's not commutative, and that's sad, but this is a different kind of interesting. Okay. All right, continuing along down the list, this one, at a glance it looks pretty boring, but then you realize a couple of things. So, it's not like we're distributing, right? That's not what's happening here, right? So this is, and it's not exactly like an associativity either, because you can't just do these in any order. Notice that that it's always kind of the same order in the cycling sense. Right? So that's weird. That's a little different and strange. We're going to make some geometric sense out of that coming up pretty soon. Lastly, now there's a property of dot products that kind of vaguely smacks of this, but if the cross product of two vectors is 0, remember if the dot product is 0, that means that they're orthogonal. It probably means that they're perpendicular. Unless one of the vectors is a 0 vector. If the cross product is 0, they're parallel, or one of the vectors is the 0 vector. So that's sort of vaguely familiar. Okay. All right. All of these statements can be proved algebraically, and that's something. And you've got the necessary tools to do that. And if you want to do that, you can go ahead. Feel free. It's just a matter of a little bit of algebra. But we're going to try to make geometric sense out of all of these also. Okay. All right. So I'm going to start off with another property of cross products. This is arguably the most important one, whatever that means. But anyway, certainly this is a very important property. If you have two vectors and you take their cross product, that cross product is always orthogonal to the two input vectors v and w. And that's a neat tool to have. If you got a couple of vectors in space, if you want to find a vector that's perpendicular to both of them, it's kind of a trick shot. right? Well, the cross product does that for you. And the cross product, don't forget, has a formula. Here it is. This formula automatically finds a vector that's perpendicular to both of the input vectors. This is, of course, easily checked. Orthogonal just means that I have to compute the dot product and make sure that I get 0. That's how you check two vectors are orthogonal. So if I want to check that the cross product is orthogonal to V and W, I just need to compute these two dot products, confirm I get 0. It's all algebra. Crank it out, no problem. They're improved, right? Now again, there's something unsatisfying about proofs that are purely algebraic because it's just symbols on the page, and now it's rigorous, and it's confidence inspiring for sure, but it kind of lacks satisfaction on an intuitive level. So I'm going to come back and address that soon. Okay, let me take a quick breath here. Does anybody have any questions? How are we doing? Everybody? Oh yeah. Mm-hmm.
So the cross product results in a vector, not a scalar.
Yes. Good point. I should have pointed that out. Yeah. So dot products are really the weirdos, right? Dot product takes two things of the same type and produces something of a different type. Cross product of a vector and a vector gives you another vector, right? Good observation. Okay. Yeah.
Can either dot product or cross product be done with vectors of different dimensions, or
no? So no, they've got to match up.
Yeah.
Otherwise, yeah, it's just it's not defined, right? Okay. So now here's some other observations. I'm going to go through this slowly. First observation: the cross product components are all determinants, and I'm going to indicate that. I guess I'll just use the same color here. But so here are the three components of the cross product. Now I've written these as components. You'll notice by doing a linear combination of the standard basis vectors. Don't forget what these standard basis vectors are. These standard basis vectors are that's 1, 0, 0. That is 0, 1, 0, etc. And I think you can see if you take coefficients and multiply out a linear combination of these standard basis vectors, look at the ones and the zeros, and those coefficients are going to be the coordinates, right? It's a neat fact. So for reasons that will become clear in a moment, I'm going to write the coordinates of the cross product as coefficients in a linear combination like this. And I claim that they are 2 by 2 determinants, and you can see that right here in these excuse me. Gosh, thank you. In these coordinates right there. They are. They are little 2 by 2 determinants of V's and W's, right? So if you look a little bit even more carefully, these are not just 2 by 2 determinants as I have written here, but these are exactly the 2 by 2 determinants that you would get if you were to be in the process of computing this 3 by 3 determinant. So these standard basis vectors, if you were to, formula for determinant, you go across the top row and you multiply, but you cross out the row and the column, there's that whole thing, right? This determinant is exactly the minor that you get when you're looking at that top left element, right, et cetera, et cetera. This is exactly what you get when you cross out the first row and the second column, and then this is exactly what you get when you cross out the first row and the third column. So weirdly, not only do 2 by 2 determinants show up with cross products, but in a way 3 by 3 determinants show up as well. And that's really weird. But algebraically, it's just a matter of writing it down. Well, oh my gosh, it works. Okay. Now, complaint. Hey, wait a minute. I thought matrices had to have elements that were numbers. What gives here? I have an element, I have a matrix, one of whose elements is a vector. You can't do that, right? So okay, fine, true. That's a little bogus, right? So you'll notice that I'm calling this a symbolic determinant. Right, so this, it's not really quite really a thing, but algebraically, if you just write it down that way and ignore the fact that it kind of doesn't really make any sense, it gives you the right answer, right? So it's pretty convenient nonsense, even if it is nonsense, right? So for whatever that's worth. Right, yep.
So in the exam, can you write out the 3 by 3 determinants when you are calculating?
Yeah, if you want to write this down on an exam, that's totally fine. Yep, I do that all the time. No problem. By the way, here's for your consideration, just another sort of vote in favor of this. Notice how orderly it is, right? That first row, 1, 2, 3. Right? The second row, 1, 2, 3. Okay, of the first vector. That third row, 1, 2, 3 of the third vector. Nice and organized, easy to remember, right? Standard basis vectors, first vector, second vector. Determinant. It's a lot easier to remember compared to the alternative. Look at this formula, right? You want to memorize that formula for the cross product? Now, it's not that you can't. I'm sure you could, right? But two things. One thing, it'd take some effort to memorize. Wait, there's 2s and 3s and 1s and 2s and 3s and back to 2s and, oh my gosh. Which way does it go? It's easy. Oh my God. Right? And that's the second concern is even though it would take effort, even I suppose you could actually memorize this, you would doubt yourself for the rest of your life. Is it V1, V3 minus V3, W1, or is it the other way? Oh gosh, which way does it go? It'd be so easy to get that backwards. And, odds are, eventually you probably would get at least one of those coordinates backwards. Okay, so for your consideration, in my life, I have never memorized this formula. And I encourage you all to copy me on that. Don't memorize that formula. Remember the little shorthand here, the little symbolic nonsense. This is really easy to remember. Takes very little effort. Once you have it comfortably memorized, you couldn't forget it if you tried. Right? So I encourage you to do that instead, yeah.
Can we just write IJK instead of E1, E2, E3?
You can. That's right. The book uses IJK. I like E1, E2, E3 because it generalizes more conveniently, right? If you ever find yourself doing an econ problem, right? And if there ever do happen to be more than 3 variables, which there will be, right? IJK, L, M, N, O, P, you run out of letters eventually. Certainly it gets hard to remember at a minimum, right? But subscripts, easy to remember. So I made this switch at about y'all's age and never looked back myself. But if you want to do IJK, it's fine. Yeah. Okay. All right. Okay. So now here's a weird one. Another weird one. Suppose you want to do a dot product with a cross product. And okay, fine. Look, we have a formula for that, and you could just write that down. And then we have a formula for the dot product, and you could just write that down, right? But is there a short way to remember this construction where you're doing a dot product with a cross product? And as it turns out, the answer is yes. And it's a fairly convenient formula. Now, the cross product, here it is. The coordinates for the cross product are there and there and there. How do you do a dot product with something? The way you do a dot product with another vector is, let's see here. Well, you multiply the corresponding coordinates. Right? So if I want to do U dot V cross W, I'm going to take these blue coordinates that I have circled and I'm going to multiply by U1, U2, U3, right? And the dot product is that expression, and then you notice, like, cosmetically, right? Structurally, the layout on the page of those symbols looks just like this one, just with U's instead of E's, right? And so it's this formula. And that lays out on the page really nicely. And so, coming back down here, this is a really nice, handy little formula for how to do a dot product with a cross product. And two things. This is an easy way to remember something, but the fact that this is structurally so simple and elegant leads one to believe that maybe this construction, maybe doing a dot product with a cross product is not just some random irrelevant thing. Maybe this actually makes a lot of sense. So they give this a name. They call this a triple product. There's 3 things in there. Okay. All right. Okay, so this is going to be a big deal formula. Now, again, notice all we did is we looked at the explicit formula for the cross product. We wrote it down in different ways and made clever algebraic observations. This conclusion here is going to be a powerful tool in helping us understand cross products. And roughly speaking, the way we're going to make this work, and this is a tried and true method in math, is find equations that relate things that you know about to things that you would like to learn about, and then figure out how to jiggle it and make good ideas fall out, right? So that's what we're going to do here. We already understand determinant geometrically, kind of. We have good sense of 3x3 determinants. It relates to volume. It relates to handedness, right? We understand the dot product pretty well, right? It relates to angles and lengths. These are all geometric things. We have geometric knowledge of everything in this picture except for the cross product. And so this is going to help us understand cross product geometrically. Okay. So why is it that the cross product is perpendicular to the 2 input vectors? Well, because of algebra. We wrote down that algebra. But remember, we complained when we wrote down the I referred y'all to algebra that you can write down. Right, to confirm. Just take the appropriate dot products, and sure enough, you get 0. So there you go, but very unsatisfying. So there's a geometric way to think about this that I think is really nice. And I want you all to take a sort of the geometric point of view on this as well. So here's one of the dot products that I need to compute, right, to show this orthogonality. If you want to show orthogonality, I've got to compute this dot product and get 0. Specifically a dot product between the 2 vectors that I'm claiming are orthogonal. Okay, but notice one of the dot products then that I have to take is also a triple product. Triple products are determinants. Determinants are volumes. And this volume here, let's just think about it. Do I have a picture of this? Yeah, this volume. Here's a picture of what that volume looks like. Our 3 vectors making up the parallelepiped whose volume we're interested in are V, V again, right, and W. And now I appeal to your geometric intuition, right? Here's 3 vectors pointing in kind of random directions. You can imagine 3 vectors defining a parallelepiped. Well, what would happen if these 3 vectors defining your parallelepiped, what if they were 2 of them were the same vector? And the answer is you get what you get when you flatten a cardboard box ready for recycling. Right? That's what your parallelepiped looks like. It's flat. There's no volume inside of the flattened box. And then you can just trace backwards, so there's no inside to that box. No inside, no volume. No volume, no determinant. No determinant. The dot product is 0, and that means orthogonal. So you might say, geometrically speaking, this is a picture of why the cross product is orthogonal to the 2 input vectors. Kind of a neat argument. I think this is worth chewing on and processing, and kind of one of the things you're going to notice about dot products and cross products and determinants and such is they fit together in a bunch of surprising ways, and I think there's a lot to be gained by playing with and seeing those geometric connections. By the way, a side note, this is also why I do the topics that are in this section of the book in the order that I do. I arranged these topics to come up in such a way that would allow me to make cool arguments like this. And I think it's worth doing that. Yeah, you gotta, yeah.
Sorry, but why is when you do the dot product and the cross product, how do you decide that the vector before the dot product is another V vector?
Oh, well, because I'm asking this question. I'd like to know if these vectors are perpendicular. So one of the vectors that I want to know if it's perpendicular is V. And the way I check if V is perpendicular to the cross product, right? Perpendicularity is confirmed by taking a dot product and making sure you get 0.
So it could have also been W.
Technically, you really need to also do W. It's going to be the same argument with a W instead of a V. Yeah, right. Okay. Yeah.
What do you mean by the notation of the parallel?
Oh, yeah. Thank you for that. So I made this up. I think this is cool notation. If it catches on, I'm taking credit for it. Right? Yeah. So the two parallel lines. Now this I did not make up. Two parallel lines typically means parallel. Right? I mean, y'all have seen that a million times. So parallel followed by a list of three vectors. This is my shorthand for the parallelepiped that's defined by those three vectors. Okay. So anyway, fingers crossed. Right. Okay. Okay, so more cool arguments. Let's look at this question here. Y'all remember this property that we wrote down of cross products. We wrote this down. It's weird. It's kind of a sort of an associativity or something, but it only goes one way. You have to kind of preserve the order. What's up with that, right? Why is this geometrically satisfying? Now again, algebra. Write it down. Plug and chug. It works, right? I mean, there's no question as to whether this is true. We know it's true. If you do that algebra. The question is why should it be true? Where is the intuitive satisfaction? Right? And the argument goes like this. Well, these are all triple products. Triple products are determinants. Determinants are all volumes. And I note signed volumes. I mean, there's the whole absolute value you got to worry about. So let's ignore the plus or the minus. We'll get to the plus and minus momentarily. The absolute values of these determinants, the absolute values of these triple products, they're all volumes. Volumes of what? Well, they're volumes of parallelepipeds. And in fact, they're all the same parallelepiped. This one refers to the parallelepiped defined by U, V, and W. Right? This one refers to the parallelepiped defined by U, V, and W in a different order, but it's the same parallelepiped. Right? Same parallelepiped, same volume. And therefore, these expressions here, they at least equal in absolute value. Now the plus and the minus, we haven't addressed that. But in terms of magnitude, these should be the same because they all geometrically look the same. Okay. Now about that order, we've already observed all of these orders are cycles of each other. Cycles always have the same handedness, and therefore we're always going to get the same sign. Okay, so same magnitude, same sign, same numbers. That's a kind of a neat argument, right? So again, it's not, don't be satisfied just thinking about this algebraically. There's great geometric intuition for why this not only is true, but should be true. Okay. Here's one of my favorite ones. By the way, these proofs are not in the book. Again, I'm doing these topics in a different order, and so the way you make the connections is different. The magnitude of the cross product is equal to the area of the parallelogram defined by those two cross product, by those two vectors. Now you might think, oh, that sounds familiar. Didn't we already know that? No, we did not already know this. We knew that the area of a parallelogram defined by two vectors in two dimensions was computed with a determinant. This is not in two dimensions. These vectors, if you're doing a cross product of them, these are unavoidably in three dimensions, not two. That old formula does not address this. And furthermore, notice we don't get the same answer. That is not a determinant. It's a magnitude of a cross product. Okay, so how to prove this? This is another proof technique that I just want to point out, if only for cultural reasons, is common in math. Sometimes if you want to show that two things are equal, find a third thing that you can show is equal to both of them. That's a common technique. Another way to say this is I like to think of this as a mathematical bank shot, like in billiards, right? We want to get over to there, and we're going to get there by going that way to start off. So we're going to start going towards something completely unrelated to what we're interested in, but it's going to give us the result that we're interested in. Notice this thing that I'm going to start with, that's not either of the objects of interest. But thinking about this third, totally different thing is going to be the foot in the door. Okay. All right, so here we go. Step 1. Determinants are triple products. Right? A couple pages back. So, first vector, second vector, third vector. Determinants are triple products. Okay, old algebra. This triple product, if you look at it, happens to also be a dot product of a vector with itself. Well, that's a magnitude squared. We already know that. Okay. All right, now, completely unrelated calculation to follow. Another thing I know about this determinant. Yeah, on the one hand, it's a magnitude squared. Sure, fine, cool. But it's also, being it as a determinant, it's a volume. Okay. It's the volume of the vector, of the parallelogram that you get by looking at these three vectors and making a parallelepiped. Okay, let's draw a picture of that volume. Let's see here. I'm going to go ahead and make that vector is that one, and then let's see, this vector is that one, and this vector is that one. Side note, we already know that that's orthogonal and that's orthogonal. We've already established that V cross W is perpendicular to both V and W. So this is not just a random parallelepiped, this is a right parallelepiped. We have, said differently, we have here an area and then this edge of the parallelepiped is perpendicular to that area. And now I'm just going to remind you of an old formula from high school geometry. Right? Area of the base times the height. Does everybody remember that old formula? This is a kind of a cylinder. It's not a round cylinder, but this is morally equivalent. An area times a perpendicular height gives you volume. Okay, so let's write that down. That purple length is the magnitude of the cross product. It's the magnitude of that thing. Right? And this yellow area is the other thing. Okay, so we're almost done. Now keep in mind, we don't actually care about this thing. Right? That's not really what we're interested in, but we showed that it's equal to this. We've now showed that it's equal to this. Therefore, these two things are equal to each other. Cancel a common factor, and lo and behold, what's left over is what we wanted. So there's our little mathematical bank shot. I think that's lovely. Everybody happy with that argument? Any questions? Okay. All right. Oh, here's a little quickie. Somebody would have been very much in the right to complain that I just asserted that determinant was equal to volume. How do I know that determinant wouldn't be the negative of the volume? Right? Well, determinants could be negative. Volumes can't be negative. We're supposed to take the absolute value. Why didn't I take the absolute value? Anybody? Yep. We don't know that yet, though. Yeah, that's a true but yet unestablished statement. Yeah. Now, there's an easier way to see that this determinant is not negative, and that is that I've already showed that this determinant is a perfect square, or it's a square, and so therefore can't be negative. Anyway, that's a little tricky thing. I think it's funny. Okay, so with this idea in mind, let's look at this. This is one of the other properties that we wrote down, sort of on our initial list of algebraic facts. And you can use algebra to do this, right? But why should this be true? Where's the satisfaction in this statement? Well, both of these statements naturally connect to this scenario of the area being 0. Right? So this connection, cross product is 0, means the area is 0. Well, that's an immediate consequence of that. The magnitude of the cross product is the area. So if the cross product is the 0 vector, the magnitude is 0, that means the area is 0. There you go. Right? So, said differently, this fact makes that connection for us. And this fact, we don't really need help on this one. Think about it now. If you have a parallelogram defined by two vectors, how is an area of a parallelogram ever going to be 0? Well, the vectors would have to either be parallel, right? Or one of them would have to be the 0 vector. Two non-zero vectors are going to make some area unless they're parallel. So that one's just easy geometry. So again, where previously we had no satisfaction, now we kind of have some geometric satisfaction. Okay. So somebody brought up the idea of right-hand order, and but let me present this as something we don't know yet because we certainly haven't established it yet. What we do know, that when you have two vectors, v and w, we do know that the cross product is perpendicular, but perpendicular could be like that or it could be like this. So how do you know which one it is? By the way, we also know that the area of this parallelogram tells us the magnitude. So we know which way the cross product points. We know how long it is. We just don't know plus or minus, is it going that way or is it going that way? Right? So which way does it go? Of these two possibilities, which one is it? Here's the answer that we already kind of worked this out. So I already know that this determinant is a square and therefore not negative. Right? That means that other than the silly case where the cross product is the 0 vector, this is a right-hand order. Right? So cross product, comma, v, comma, w. The determinant's positive. That means a right-hand order. Now, of course, that's not exactly the most convenient way to think about it, but let me cycle like this. Cycle that first vector around to the end, and what you have is this is a very handy way to think of sort of resolve that question. If you have two vectors v and w, do the whole right-hand rule thing. Index finger along the direction of the first vector listed. By the way, let me emphasize that the first vector listed, the first vector in your cross product, that's the one that you've got to do first, and therefore with your index finger. The second vector of your cross product, the one on the right in your cross product, that's got to be second in your list. Right? So left vector first, right vector second. Your thumb will point in the direction of the cross product. Yep.
Does this mean that the determinant, if you switch just w and v to the determinant, would result in negative?
Yep.
Times length of v?
That's exactly right. Yep, absolutely. Okay, so now we have a perfectly well-defined answer. I know exactly which one it is. Now it's the problem is this being a two-dimensional piece of paper, and these are three-dimensional vectors. It's hard to for me to point to exactly what I'm intending here. But I was trying to draw V kind of like this, W then going into the page, and that being the case, my thumb, you see, indicates that the cross product has to be this one. And of course, it's hard to. If you just kind of flip it in your mind, you could see W coming out of the page or something. That wasn't my intention. Okay. All right. Okay. So this is what I like to call a completely geometric characterization of the cross product. By the way, you could, I suppose, present the cross product starting off very first thing with this. This is all geometric, right? Perpendicular, area, length, order. It's all geometric talk, right? And this is a perfect characterization of the cross product. The cross product is the unique vector that has these three geometric properties of its orthogonal to the two inputs. Its magnitude is equal to the area of the parallelogram. And it makes this a right-hand order listing. So, like I say, you could start with this, and then through some, not entirely unrelated arguments, work kind of backwards and derive the formula for it. But I think that's a little bit awkward. It's a lot to ask for students to look at this geometric description and say, "Oh yeah, no, cool, that makes a lot of sense." Right? So that's why I don't do that. But anyway, yep.
Isn't it also true that the dot product is the area of the parallelogram?
Nope.
No? So what's the geometric dot product?
Dot product is a component. If one of the vectors is a unit vector, I'm not sure what you're thinking about.
I thought there was like I thought there was a shape that like the dot product was the area. Is that not true?
Nothing comes to mind. Yeah, if you find something along those lines, let me know, and I can take a look at it. But yeah, right. No worries. Okay. So and there's a point of view, by the way, on and I'm not going to go through most of the rest of this page because it's just kind of it's algebraically writing down something that's much easier seen as a hand wave. But why is it that the cross product is anti-symmetric? I mean, where's the satisfaction in this? Right? I mean, algebraically, you can look at it and numbers algebra says what it says, and so it is, right? But why should this be? And here's a really easy answer. If let's suppose there's V and there's W, right? So VW. V cross W has to point that way. Keep in mind, VW, right? So V cross W points that way, but VW, W cross V points that way, right? So switching these two vectors is naturally going to make your thumb point the opposite direction. So that's why that minus sign actually makes great sense, right? So there's a picture of why that minus sign comes up. Yep.
So in the notes you said as desired when you switch it, so is that also how you could do it, like?
Yeah, I mean, if
this way,
you can, this, I'm going to just, you can talk to me about this after class. I'm just in the interest of time, I don't want to get into these are kind of weeds that I sort of regret, to be totally honest. Yeah.
Okay.
So I'd rather make this case. But if you want to talk through this, we can. Just come talk to me after class. Yeah. Okay, so, real quick example, just to show you how you can use the geometric properties of the cross product. I'm going to compute this cross product without using the formula. Just by making geometric observations. So E3 cross E1. Now let me draw a picture over here. Here's my axis system. I want E3 cross E1. Okay, E3 is like that. E1 is like that. How am I going to find the cross product? Well, I know that the cross product is parallel to that line, because that's the line that's obviously perpendicular to E3 and E1. All right, geometric sense tells me that. Right? Now, how long is it? Well, the length is the area of the parallelogram. This parallelogram is easily seen to be a square. Length is the area of the parallelogram. Again, a square, which is clearly 1. So I'm looking for a vector of length 1 that points along this line. And which way does it go? Well, again, right-hand rule, right? So E3 cross E1, E3, E1. Look at my thumb. My thumb tells me which way to go. Right, my thumb tells me that this cross product has to go that way of distance 1, and there is only one vector of magnitude 1 that points in the positive direction along the y-axis, and that's E2. 0, 1, 0. Everybody on board? So I didn't do any algebraic calculations. They're purely geometric argument. Okay. All right. Okay, so moving along now to lines and planes. So this is, I think this is section 1.4 at this point. I've sort of lost count. I think that's right. So I want to start off with flashbacks to Algebra 1 class a long time ago. I hopefully want to fill in a little sort of gap in how lines, what's the equation of a line in the plane? Right? There's a kind of a gap in the way that gets presented in Algebra 1 classes, and it's not their fault. There's nothing they can do about it. But First, a quick reminder of what an equation of a curve is, the equation of a shape. I just want to point out, and I'm going to come back and make sense out of this in a little while. It's a test. So please make sure to have this intuition in your mind. The equation tests points. If you have an equation of a curve or equation of a surface, we'll talk about later. If the point satisfies the equation, then it's on your shape. And if the point does not satisfy the equation, then it's not on your shape. Right? And y'all have used this a million times, right? I just wanted to point out, as a reminder, that's the relationship between the equation of a shape and the shape itself. Okay. All right. Now back to Algebra 1. Here's a line. Yawn. Right? My gosh, what is this? 8th grade? I mean, this goes way back. Here's what in 8th grade was my favorite equation I don't know why I was ranking my favorites, right? But this is my favorite equation for a line in the plane, right? I liked it better than this one. I'm just going to put a frowny face on that. I liked it better than that one because of the geometric satisfaction, right? So for example, this point there, the intercept, right? You can see it in the equation. It jumps out at you. That's the nice thing about that equation, right? And then likewise, this slope here, right? And I just represent the slope like that. That slope is, again, it's represented in the equation. Where is that over here? Where is the slope in there? No, it's not there. Where's the intercept? It's not there. Right? So, it seemed reasonable to me that this is the better one. I am now entirely the opposite of that. This is now my preferred equation for a line. Right? And this is the one that's like, it's not I'm just going to do about like that. I don't hate it, right? It's nice for its uses, but it's much more useful to write lines like this. So let me try to persuade you why that is. I'm going to try to give you geometric satisfaction of these coefficients A and B and kind of C a little bit. Okay, so the way we're going to do that is now forget this whole setup, pretend like we never saw that. Right? I want to describe a line. How would I go about describing a line? What defines a line? And I'll point out that if you give me a point on the line, now that's not enough. There's lots of lines that go through that point. That point does not define the line. But if I then further give you a vector perpendicular to the line, well, now it's uniquely defined, right? There is only one. There is exactly one line that is perpendicular to that in vector and that passes through that point x0. Okay. All right. And with this information, I'm now going to create a test. A way to test, points. How would I decide if a point X, is on the line versus maybe it's not on the line, right? How do I distinguish a point that is from a point that isn't? Where's my algebraic test? Okay. All right. So here's the idea. That point is on the line if and only if that difference vector is parallel to the line. Now, geometric appeal, right? If the point is on the line, then x minus x naught, that's what this is parallel to the line. Whereas, if the point is not on the line, then x minus x naught is not parallel to the line. That's not parallel. So this purple vector here, x minus x naught, whether it is or is not parallel to the line, is simultaneous with whether that point x is or is not on the line. Okay. And so let's write that down. On the line, if and only if parallel to the line. Parallel to the line means perpendicular to that in vector. Don't forget that in vector is pointing that way. So if you're parallel to this, then you're going to be perpendicular to that. I want you all to try to develop an instinctive knee-jerk move that when you see two vectors that are perpendicular, I want you to instantly, in your mind, think, that means the dot product's 0. Right? That allows you to jump, you'll notice, from geometry talk to algebra talk. Right? And it's all over from here. But this, distribute the dot, move some stuff around, you get this. Don't forget that our in vector has, this in vector here has got some coordinates. I call those A and B. Excuse me. And then this x vector has coordinates x and y. And so the dot product here in dot x, you can see it right here. It's ax plus by. That's how that dot product works. Ax plus by. And now what about this dot product here? Well, it's some number. Whatever. I'm just going to call it C. It's a number. It doesn't have any x's and y's in it. N is given. X naught is given. That dot product is fixed. Okay. And there you go. There's your old Algebra 1, that alternative equation for a line. And so back to the question, why should I care? Why should I like this equation? What can I get out of this equation? What can I, at a glance, determine about the line just by looking? And the answer is, I've got right there in the equation of a line, this this in vector. Little n. And that's really neat. And this is a lot less interesting most of the time, as it turns out. Right? Being able to see the vector over here is really cool. Vectors are things we can do dot products and stuff with, cross products sometimes, and so very cool. Okay, so yeah, this is how you write it in an Algebra 1 class. But really, again, vector notation is pretty convenient in a lot of circumstances. So most of the time, it'll be written like this. I would encourage you to memorize this one: n dot x equals n dot x naught. And of course, it's trivial to multiply that out if necessary, but it's valuable to be able to see specifically how these players show up in the algebra. That vector there, this A and this B, those are telling you the coordinates of a vector perpendicular to the line. That's meaning. Right? This number here, whatever that is, that's the dot product between these two givens that we're defining the line in the first place. Meaning. Okay. All right. Now, so we've polished off your Algebra 1 experience just a little bit. That was not my goal here, but yeah, go ahead.
So we're saying that the n vector is A, B. What exactly does that mean?
It's a vector. Vectors have coordinates, right? So that's got certain coordinates. I got to call them something.
I know, but how can you define a vector with just two coordinates that is started from the origin?
It's a vector in the plane. Vectors don't have locations. Vectors don't start anywhere. Vectors are directions and magnitudes. Okay. Right? So that's an important idea to digest, right? So if you want to talk about where something is, now you're talking about points, right? Very importantly, I'm not saying anything about where this is. That vector is just as meaningfully there or here or whatever. Direction and magnitude is all that is.
So they're all perpendicular. It doesn't matter because they're all perpendicular.
Well, these arrows that I've drawn are all perpendicular, but it is in fact just one vector. Right. So that one vector, I've drawn the arrow 4 times, but that's one vector. That one vector is perpendicular to the line.
Right.
Yeah. Right. Okay. Oh, by the way, and that does remind me, I slipped up and used a word that I hadn't defined yet, but the reason that I call this in and not, Q or something, is because it's commonly referred to as a normal vector. Normal in this context means perpendicular. Normal is a weird word. Normal gets used in lots of different ways in math. I one time counted 6 completely disconnected meanings of the word normal in different contexts. Anyway, sorry about that. If you've ever taken a stat class, you know about normal distribution. It's got nothing to do with this. Mathematicians are just not verbally creative, I guess.
Wait, so are A and B just the x and y components of the normal?
Yeah, that's right. A and B are the coordinates
the first and second, let's call them first and second coordinates of the normal vector. That's right.
The coordinates are just the components?
Yeah, it depends on how you use the word component. They're components in the direction of certain standard basis vectors.
Okay.
Right? Yeah, that's right. Okay. Okay, so easy, quick example. Wait a second. No, we're out of time. Well, y'all can read this easy example on your own, but we are out of time for today. We'll pick up here on Wednesday. Don't forget, we are taking attendance starting on a Wednesday. So see you then. You can come talk to me after class.